How's it going, guys? Welcome to another Soul Encoded tutorial. Today we're going to be covering the solutions to the closures and recursion challenges. So looking at the screen right now, I'll bump it up a little bit, but I'm on the write up. I have copy and pasted this particular for loop. Now there's an error with this for loop. Let's run it. So if you notice here, the for loop loops over this particular function 3 times, but it prints three times, like you see. So what's going on here? So set timeout, for those of you guys don't know, set timeout is just a method in JavaScript that allows you to perform functions afterwards. So the set timeout like archetype is kind of like a callback here. It expects a callback there, a callback function, and then it expects the milliseconds, so like 100 milliseconds, and that's it. Yeah, so that's essentially what set timeout function is. So what's going on here? So in JavaScript right now, what is happening is this particular code base loops 3 times, and then because every time it loops, this I variable, because it gets hoisted to the top, it keeps getting updated every time it's getting iterated. So it's at the end, when the set timeout is ready, the code has executed already 3 times. The loop has executed 3 times already. Therefore, the value I is 3 when it gets logged 3 times by that callback function. So that's essentially what's going on. So how do we solve this issue? How do we make it so that we could keep the same kind of code base, but at the same time change it in a way so that our I prints out as intended from 0 to like 0, 1, and 2, and 3, etc. Right? So the solution is to enclose the lexical scope value of I into the set timeout function, right? So we're gonna be using closure. Obviously, we're always gonna be closing. So let's also, in this particular example, I'm going to solve it by using an iffy, which is an immediately invoked function expression. Right. So we went over that briefly in the lesson, so watch that if you're confused about it. But all it is we're going to write a function expression like so. We're going to pass in, let's pass in a local I, just to say so. And then we're going to move this entire block of code that essentially has our code base right into the function expression. Now at this point, this is a function expression, but it hasn't been invoked yet. So to do that, there's 2 ways. You could do this, or you could do that. I prefer the dangly balls method, but there you have it. That's the immediately invoked function, because the function expression was defined and it has immediately been invoked. We also have to make sure to change local I here. Also remember that we need to pass I into this expression, function expression. So this I will be local I when it's getting executed, and therefore will be printed. There you go, 0, 1, 2. So that's pretty much what we expected it to happen, and that is how you solve the always be closuring problem. Moving on. So I copied this. It looks like we need to create one function called create base that takes an argument, and when you call it the first time, it returns 7, and then the second time, if you call it with 10, it returns 15. So it looks like it just has a base value that's set. So let's create that using closures, right? So let's say var create base equals function. So let's create, after we finish naming the create base, let's make sure we pass it an argument called base, because that's basically we're creating a function that has a base number attached to it. So we'll say, and after that we'll create a function called var, and it looks like it's an add function, right? So add equals function, and then here we'll return x plus the base. we need to make sure to return the add function. Return the base. So now when we assign the create base to add 5, and add 5 is, we'll call our add function, which passes in the value 2 for the x argument here. And because the base right here has been defined up right there in the original invocation of the create base, that base is available as the lexical scope of this add, and that's why it's able to use that lexical scope base equals 5 to create this new value. All right, so let's give that a try. We forgot to log it, so let's log it. Let's run it. 7 and 15. And there you have it. Moving on. Recursive problems. The next problem is the Fibonacci problem. Now, I'm going to copy and paste the iterative version of this just so you guys can see what it looks like. So so what is Fibonacci? Fibonacci is just a sequence, as I explained in the write-up. But all it is for any nth Fibonacci sequence, it's a summation of the previous numbers. And then each sequence is created by adding up the previous 2 numbers. So that's a Fibonacci sequence. And it creates a shape kind of like this circular motion. And you see this in the wild all the time. It's actually a really cool sequence. So let's go ahead and try to solve the Fibonacci recursive problem. Let's go. Let's write function fib for Fibonacci. So let's pass in the value n first. Now let's try to solve the base case. Basically when n is less than or equal to 2. So that's like the point at which we can't go any further back, right? Because Fibonacci requires at least 2 numbers before the current nth number to create that sequence, the first problem sequence. So anything below or equal to that, that's the point at which the base case occurs. So let's say n is less than or equal to 2. And at this point, we know that the value for both of these base cases are returned is 1. So we just return 1, right? And that's because we're looking at here. So right there, that's like the base case, right? So the next part is to solve the algorithm portion of it. So how do we solve the smallest problem first? So I already mentioned that to solve Fibonacci nth Fibonacci sequence, you take the current sequence is basically n minus 2, the current sequence minus 2 plus the current sequence minus 1. So basically n minus 1 plus n minus 2. That gives you the current sequence. So that's the algorithm. So let's just return that algorithm. So we call fib, and then we say n minus 1 plus fib n minus 2. Okay, let's console log fib 10. And because we have already gone through the iterative process of finding out what fib 10 is, we should be able to verify this. So let's go ahead and try. And it's 55. So there you have it. That's how you solve recursive problem. Now, like this portion and this portion, those all come with practice. You know, once you start thinking about these problems, you'll start to see, okay, that's the base case. That's like the point which it should start calling the stack back up and go back up the call stack and then return the value. Okay, that's how you solve that's how you solve the problem once. Yeah. But yeah, so those are the challenges for this particular functions video. I hope you guys enjoyed it. Comment below if you feel like this was not enough. Thanks for watching this video, and I will see you guys next time.